Hey, we are back and we are going to do a quick video on a linear regression t test. In my previous video, I walked you through how to do a linear regression t interval and check all the conditions. This one should be a lot quicker because everything's the same, except now we're doing a t test where we're running a test to estimate the slope of the true population regression line. Okay. Again, our test statistic is always going to be statistic minus the parameter divided by standard deviation. This doesn't change whether we're doing z-scores or t-scores. In this case, we are going to be looking at a t-score because we're looking at a t-distribution, where our statistic is b, which is the slope of the sample regression line, minus beta, which is the claimed hypothesized parameter, which is always going to be 0 because we're going to assume that the parameter is 0 unless stated otherwise. And then divided by our standard error of b, which is the standard error of our slope, SE sub b. And we're looking at a t-distribution with degrees of freedom n minus 2, and this will help us find our p-value. Okay. So as always, we can do a one-sided test or a two-sided test. This test can be done in your calculator. However, it's usually not. It's usually done in a Minitab output. So in this video, I'm going to show you just how to do it in Minitab output, and then maybe I'll show you quickly on how to do a regression test on a calculator. So here we are. This is the data that's given to us. It says infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of the rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured the intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years old using the Stanford Binet IQ test. The table below contains the data from the sample of the 38 infants. This is a very intricate test. So instead of us putting in this data, they give us the data, but we're actually going to use what they give us from the output. So it says some computer output from a least squares regression line gives us the output below, and here it is. This is the regression line. There's a scatter plot in the regression line. Okay, so this is cool. Looking at this, yeah, it looks fairly linear, but again, we can't confirm that. Maybe an outlier up here. Doesn't look great, but we'll see how our residual plot looks. Here is the Minitab output. Here is the residual plot, and here is the normal probability plot of the residuals. How do I know this is a normal probability plot? Because the y-axis is the expected z-score. And that's what residual normal probability plots are. They are expected z-scores versus some set of data. In this case, my data set is the residuals. Again, this is my y-intercept. It's the coefficient of the constant. This is my slope. So this is the coefficient of the variable, which is the cry counts. We have the standard error of the coefficients. Now, this one, 8.934, we don't use. That is standard error of the y-intercept. The one below it, the 0.487, that is the standard error of the slope. That's very important. That is SE sub b. Okay, so part A, it says, what is the equation of the least squares regression line for predicting IQ at age 3 from the number of crying peaks? Interpret the slope and y-intercept of the regression line in context. So again, here is the y-intercept. Here is the regression line. Let's go ahead and put that into context. So we have the predicted IQ scores, or you can do IQ score with a hat over top. And then we have the y-intercept and the slope. And then, of course, our variable is in terms of cry counts. We don't just use X, we put it in context. The slope in context, it says for each additional crying peak in the most active 20 seconds, the regression line predicts an increase of 1.5 IQ points. So what they use 1.5, it's really 1.4929, but this is the slope, and it's every increase in 1x increases in that many y. So every increase in 1x, x being the cry count, then it increases in 1y, or 1.5y, which is our y value is the IQ points. The y-intercept predicts that an infant who doesn't cry when they are flicked has an IQ of about 91 or 91.268. Okay, because that would be when the x value is 0. Part B says, explain the value of S and what does it mean in this setting. Again, S is the standard deviation of the residual. It's your typical prediction error. So in the context of the setting, it is a typical prediction error when using the regression line in part A. So when using this regression line, it's on average how far off you will be from the actual IQ score. Okay? Versus the predicted IQ score. In part C, it says, does this data provide convincing evidence of a positive linear relationship? Okay, so now, because we're looking at just a positive linear relationship, we are assuming our null hypothesis is that there is no relationship. So we are assuming beta equals 0. And we're looking for a positive relationship, so our alternative would be beta is greater than 0. Okay, we're going to use a significance level of 0.05 because they didn't give us one. So this would give us evidence that the beta is positive, so it would be a positive linear relationship. Okay, so we have checked the conditions. If the conditions are met, we were able to do a linear regression t-test. Again, they call it t-test for slope. It's easier to call it a linear regression t-test. Call it what you want as long as you have a t-test in the word regression or beta or slope in your answer. So is it linear? Again, we got to use the data that's given to us. They give us a residual plot. They give us a scatter plot. So we got to use those two plots given to us. So because the scatter plot suggests a moderately weak but positive linear relationship, and the residual plot shows some randomness, there's definitely not a pattern in a residual plot. It's not a great looking scatter plot, but it does show at least some sort of linearity. Okay, independent, we are sampling without replacement, so we got to assume there are more than 380 infants in the population. Normal, again, we are looking at to make sure our residuals are normal, so we are referring to this normal probability plot of the residuals, which is this one right here. Now this looks fairly linear, so that's good. So it says the normal probability plot of the residuals, so slight curvature but no strong skewness or any obvious outliers that would prevent us from using a t procedure, so we can continue on. Equal standard deviation. The residual plot, which again I don't love, but it shows fairly equal amount of scatter above and below the x-axis. We have that one possible outlier, but it's fairly equal, so we can continue. We checked it, and then random, we're told that it's 38 randomly selected infants. So that's my state and my plan. Now I'm going to my do section. This is where I told you that we're going to need this T and this P. So in our do section, you need three things. You need degrees of freedom, your test statistic, which is a t-score, and your p-value. Our degrees of freedom is going to be 36 because there are 38 infants. So it's 38 minus 2 is 36. Our t-score, so we see where it says t, and then because we're looking to estimate the slope, we go down to our slope variable, which is cry count. This is our test statistic, 3.07 is our test statistic. This 10.22, we don't do regression on y-intercepts. We don't care about a y-intercept. We care about slope. So 3.07. This p-value they give you is the p-value for a two-sided test. It is a p-value for a two-sided test. So if we were doing a two-sided test, our answer would be 0.004. However, we're doing a one-sided test. So we got to take this p-value and cut it in half. So our p-value is actually 0.002. So in our do section, so here's our state plan. Our do section, we have a p-value of 0.002, degrees of freedom of 36, and our test statistic of 3.07. It says look in the T column from the computer output across from cry count. So it gives us everything we need. We just have to be able to pull it from the output. And then because our p-value is very small, then we are going to reject the null hypothesis. There is convincing evidence of a positive linear relationship between the intensity of crying and the IQ score. And that is a linear regression t-test. If we wanted to do something in the calculator, I'll show you quickly where you can find it. Again, very rare to actually have to input data because usually they just give you an output, a Minitab output. But if we needed to use the actual calculator, we would go to our calculators. I still have the data in from the interval about the Ford F-150s. So my t-test would be about the Ford F-150s. That's okay. I would go into stat. Come on. Stat. Go over to test. Go over to test. Go down to linear regression t-test, which is Lin Reg T Test. There it is. Hit enter. My data is in list 1. Y list will be in list 2. We are doing a what was it, greater than 0, right? Yeah. And I would hit calculate. And again, I'm not doing this is very different than what the data that I have in here is not the data that you looked at. So don't look at these numbers. However, we can talk about what's important here. First of all, beta. This is what we're talking about. This is rho. We don't talk about rho in this class. Rho is something that is a variable that you would look at in a higher level stat class. This is our test statistic. This is our p-value. This is our degrees of freedom. This is our y-intercept, our slope, and our standard deviation of the residuals. If we keep going down, you will find r squared. You will find r. That's it. Okay. So if you actually had data, this is the test that you would do. But a lot of times, you'll just be given a Minitab output, and you have to interpret it. Okay. Have a wonderful day.